Hi, everybody. My name is Kyle, and today I'm going to be talking to you about scaling for real people, a presentation I like to call Between Toothpicks and Steel. Now, this presentation that you're not going to get code samples out of it. You're not going to get tips to tune a query. You're not going to get any specific technology advice here. What you're going to get is an overview of kind of how humans tend to look at scaling and kind of the behaviors that surround that. So it's a little bit of a talk that you will probably take something away from, but it's probably not something that you'll want to directly integrate into a project, but rather how to behave when you're thinking about a couple different things. So let's talk a little bit about who I am. My name is Kyle, like I said before. I do work for Amazon Web Services, AWS, and I work specifically on the Open Distro for Elasticsearch project, which we'll get to in a second. I'm based out of Edmonton, Alberta, Canada, which is the northernmost city in Canada. It's starting to get a little chilly outside, as you might imagine, but it is great because I get the whole winter to do the sort of things that I love. Kind of cooped up inside, but that's fine because I spent most of my life writing software and I love doing it. It's almost a compulsion for me. I love working with technology and specifically how you can use software to yield that into something useful. Now, my areas of interest tend to go around um, the intersection of data and software. So in that case, I'm not really that interested in writing some bit fiddling device drivers or anything like that. But if you tell me to take a big pile of data and a little bit of source code and come up with something useful, that's something that is a really great project for me. So that does integrate into what I do right now. Previously, I've worked with other technologies like Redis, but right now I'm working with Open Distro for Elasticsearch. You might ask, what is that? I'll tell you. This is most of the presentation will not be about this, but I do want to give you a little bit of background on what I am and also a slight commercial for the project that I'm attached to. Open Distro for Elasticsearch is somewhat self-explanatory. Open meaning that it is an open source project. It is not related to the Amazon services that have anything to do with Elasticsearch. It is a distribution. Um, this is a little unusual for software outside of something like like an operating system. But a distribution here is basically we're taking a collection of individual parts, combining them together, and giving you a way to use them all in concert. And then it is based on Elasticsearch. So all these together gives you these four things. A gratis and Libre version that you can use. Gratis meaning that it is completely free, it does not cost you any money, and Libre meaning that it is unrestricted in what you can do with it. This comes from the Apache 2.0 license that is featured in all the software that's included in the distribution. It is really a great way to get started in this without having to have a lawyer review any type of licenses or anything like that because it's standard Apache 2. It's a really feature-rich distribution. Now, there are individual pieces you can get out there, but they lack a lot of the features that you'd need to actually use it in any given capacity. So this kind of bundles all these features together in the things that you would really need to use to have it in a useful state. It is a community-driven project, meaning that we are actively looking for the community to talk to us about what they need and what they can add to it. So this is, in the true sense, open source, and it's enterprise scale. So this is not something that you could only work past a certain amount. This does kind of go over with the topic a little bit as far as scaling. This is something that is used pretty widely at very large organizations, and including things that are not just a trivial amount of computation. So now we've got that out of the way. You know who I am. You know what I do. Let's talk a little bit about bridges. This is where we kind of get into the title of the presentation. Before you have a rope and wood bridge. Now, this will probably be terrifying to most people to think about crossing it. Anybody who has a fear of heights would probably not like this picture so much, but it is a good example of a minimalist bridge. It is spanning two areas with a gulf in between it. and it is made of, looks like rope or some very minimal kind of steel cords and wood. And the wood doesn't even cover the entire base of it, the entire floor. So when you think about this, this is something that's designed and it serves its purpose. It allows the person you can see in the shadow here to cross the bridge, but it also is doing it effectively, right? This person has crossed. It looks like they are going away from us. So it has worked. But it's not designed for motor vehicles. It's not designed for trucks, and probably not even for a crowd of people. Now, let's contrast this with another bridge. This is, I believe, the Brooklyn Bridge. I will be talking about another bridge in New York City later in the presentation. This is the only one that I could find a good image of that I could use in the presentation. So this is a very different bridge. You can see here, just from a very quick glance, that it's made of stone and steel, and there's concrete involved. And you can tell as well that it's not a simple thing. This probably took many years to engineer. It is handling motor vehicle traffic. These are two things that are the same application, but very different details and very different use cases, even though they're both spanning an area between, something between it. So this is actually a pretty good metaphor for how we build applications at scale. Let's deep dive a little deeper into another bridge. In this case, we're going to look at the George Washington Bridge. Now, this bridge is in New York City. It is between Manhattan and New Jersey. It was built between 1927 and 1931. And then they added another deck in 1959. So it has two decks. It's a suspension bridge. It has a lot of materials involved with it. I got some stats for it. I'll read these off now. It's 105, 986 cables that make up the suspension part of it, which would be 137,000 kilometers if you were to kind of stretch them out and not bundle them together. It is 184 meters tall, and if you were to put the rivets in it, it's 475,000 rivets, right? So, really big thing. So, the other thing to know about it is that it's the busiest bridge in the world, motor vehicle bridge. It handled 103 million vehicles in 2016. That's a lot of vehicles. The whole thing was quite a feat to build it. You have steel driven directly into bedrock. It cost over $1 billion in inflation-adjusted figures. So it was not cheap, very costly. And it really scales. I was able to get some information about this from this website on screen. And if you take a look at this, this is the hourly traffic. I think this is an interesting thing, and we'll get into how this kind of maps to the software we're building. But if you can look at the one side of this, you can see that at 2 a.m. it's handling less than 2,000 cars per hour. Now, in just a few short hours, when you get to 6 a.m., it's at its peak where it's handling over 10,000. So it's really handling the scale, right? This works a little differently than software. We'll get into that a bit later. But the important thing to know here is that if we were to kind of compare it to software, we'd say, oh yeah, that scales. It's handling the scale quite well. It's not buckling under pressure. And that may or may not be something that we want to take into account. So let's move it back into our domain a little bit. Let's say two software architects were asked by their boss. You can see her in the foreground here. She's a little bit out of focus. And then we have our two software architects here having two opposing views of how to build a bridge. Now, the boss comes in and says, hey, we got to build this bridge, right? And it's a real bridge, but you guys are engineers, so why don't you actually build it? So in this scenario, we've got the stock photo here. I think it's really fitting, actually. I can tell a little story around it. The boss says, we don't know how many cars will actually be needed to handle it, but it could be high or it could be pretty low. Now, first approach is this guy in the foreground. He's on his iPad. You can see him looking directly at his boss. Uh, he takes the point of, let's take a look at some of the best practices, right? He does some research in the area, and he says, looking around, we could build something just like the George Washington Bridge, this bridge we were just talking about. It handles traffic, it scales. No matter how many cars we throw at it, it's going to work great. Now, the guy in the background on his laptop, I love his look on his face because he's kind of like, yeah, whatever, dude. And he's saying, I just walked across this bridge. It was made practically of toothpicks, and it's super easy to build. Anybody can build it. We don't need any special machinery, and this will work fine. Now, given the example from the boss, she might think, okay, well, we have two different things here. We have somebody, the guy in the closer to the camera, who is advocating for building basically a copy of the George Washington Bridge. He's basically saying, I read up on this. I read an article, or I looked at what somebody else is doing, and I want to copy that, right? That's a great way of looking at it. The guy in the background, however, he has a different view of things. He's basically saying, hey, I got something running on my laptop, and that works for me. Two classic cases of over and underestimating. So let's evaluate that for a second. Humans are actually really bad at estimating. This is something that I think we've all kind of felt, and I'll give some reasons why. One thing is humans are really bad at understanding orders of magnitude. Let's take an example using time. You can use anything here, but time is just an easy example. It could be data, it could be, traffic, it could be anything. So, but this is a good example because it's something we all deal with every day. It's time. 1 second. We understand 1 second. 1 second is easy to understand. Now, 1,000,000 seconds, you might think, okay, that's a lot of seconds. How long is that? 1,000,000 seconds is actually about 12 days. So you can think of that as like your vacation time, right? So it's something you can feel, you can understand that. Now, the difference between 1,000,000 and 1,000,000,000 is a lot. And some people might say, well, 1,000,000 is a vacation, 1,000,000,000 is probably several vacations. Well, actually, it's about 30 years. So 1,000,000,000 seconds is 30 years. That's your entire career, right? Now, if you were to go one step further, 1,000,000,000,000 is 30,000 years worth of seconds. That is longer than human civilization. So we kind of get to a point where we just look at a large number and say a lot. And we can't really easily understand it without doing some sort of comparison that gives us some sort of context. This is an example here. The other thing is that humans have a really finite perception of time. This is something that I discovered years ago, and I think it's a really useful exercise for people who are building software to understand. So not only can we not understand orders of magnitude, but if something gets really small, especially when we get into time, which is important when we're talking about scale or whatever response time, we have almost no understanding of anything below 100 milliseconds. Now, this is something that is relative. When you look at humans who are younger, so children, they have a little bit better response time here than adults or older people. But really, 100 milliseconds is this kind of instant threshold. So if you start thinking about something taking 80 milliseconds or 90 milliseconds, that's a difference, right? But if you are kind of just using something, you'll have no concept of the difference between 80 and 90 milliseconds, even though it represents a pretty significant perception of time. And in fact, if something takes 1 nanosecond, you don't understand that difference between 100 milliseconds and 1 nanosecond. So taking the magnitude and the perception of time into account, we're completely out of our bounds in perception. So when we're thinking about scale or estimating scale, we can't really do it very often because we're bad at magnitude, we're bad at time. So the other thing is less about humans' ability to do something, more about kind of what we think of and how our behaviors are. It's this idea of the planning fallacy. Now, in the late 70s, there's two researchers that kind of came up with this overall idea that planning was a fallacy. Kahneman and Tversky in 1979, to give kind of the quote here, we underestimate even when it contradicts our own experience, which is kind of crazy. There's a few things that come into this. There's a whole planning fallacy. I would encourage you to look it up. There's a whole amount of research around it. But two ones that I think are important when we're talking about estimating and building software are the idea of planning or plan anchoring. This is basically that we take heavier weight to information that comes earlier on in the planning process than later. So if we have something that early information says this, and then we have something that contradicts that, we make insufficient adjustments to our plans to really accommodate that. So this is something where we often fail to account for the actual differences that we will have when we're trying to estimate for scale. The other thing that goes into the planning fallacy is social pressure. Social pressure in this case is basically we want to please people, and we also don't want to look like we are going back on what we said originally. So there is social pressure to maintain plans when oftentimes they will be presenting us with alternate information that is contradicting. Now, the other thing to look at when dealing with this is optimism bias. About 60%, excuse me, about 80% of the population has a bias towards optimism rather than pessimism. The thing to keep in mind here when it comes to scale is that scale and success is often not public. So if you are looking at examples through the rest of an industry and you say, company A has very high scale or company A is being successful or both, these are things that we probably don't see the failures that come into this. So they may have failed or they might not be at the scale. Scale can be a closely guarded secret in business. And we may be getting a false perception of that. So this is playing into our optimism bias. The other thing to do with it is scale has little to do with public awareness. I think this is something that we will go towards optimism rather than actually evaluating what we need to do by looking at kind of a public awareness of the people who are doing something. So a project may be completely invisible to you and it might be really high scale, where another project is very visible and you don't really understand the scale, but you might think this is where the best practices come from. So there's really these tricky things when you get into estimating, right? We can't perceive a lot of this stuff, and we're taking the wrong information into account to develop our plans, which ultimately create a scalable application. Now, I have a few kind of things that I want to highlight. I want to highlight fashion in software engineering. This is something that you kind of see, and you will start seeing once I explain it to you. Now, before you have a nice stock photo that I was able to get the rights to, and it is a very trendy looking a woman. I'm going to, from my middle-aged adult male point of view, I'm going to say she looks very trendy. I don't pay attention to true fashion trends, but I will say that when you think about this whole idea of fashion is often not necessarily about utility, but about what is being pushed by a number of organizations. So the fact that she has a particular color of blazer there is dictated by fashion, not necessarily by utility in the most case. So I want to also divide out fashion from trends. Trends are totally okay. Trends actually are just a representation of where people are doing something or how people are going with something. So that's fine. Example of a software development trend might be statically typed languages. That's fine. Those are getting more popular. People are using them. Now, fashion is a manipulation of a trend to sell you something, just like the color of the blazer that this woman is wearing. You can think about things like, the cut of a pair of jeans really has nothing to do with whatever, right? Now, taking this back to software development. In software, you have problems and you have to solve those problems, right? But the problem with this is you're also not working in a vacuum and you are being marketed towards even if you don't really realize that. So many of your choices may have been influenced by those who are trying to sell you something in software. So you might be seeing and reading an article that is actually being commissioned by someone to tell you that you need something. Now, there might be many ways to solve a problem, and because one is being kind of funded, of course, that's the one that you're seeing more often. Now, some of this is fine. I will say this is, and I personally worked in this industry for a while, so I participated in this. The benign situations is where you're telling people about something that's out there, and then you are letting them make their decision if it matches their use case. But this can be trickier sometimes. So in good faith, that's what you're doing. In bad faith, it's trying to sell people things that they don't really need. So in that case, it's really important to understand the dynamics here. Software fashion oftentimes is marketed towards the largest organizations or the organizations with the largest budgets. So you will see in the kind of discourse online about software that stuff that gets the most coverage is things that are actually being used for the largest organizations. And those are things that you may or may not need. It's important to start to evaluate when you're looking at the discourse that's happening, what is actually being pushed on you, and really take a critical eye of that. If something is being pushed on you, is it something that you truly need or is truly good for your software project? When it comes to scale, oftentimes this will lead to an exaggerated sense of your own scale, right? Because people are marketing these very, very large products that are towards these very big budgeted organizations. So keep that in mind. Just keep it in the back of your mind and take a real critical eye on anything that you're reading in the discourse. On a more technical note, know the location of the walls. What I mean by walls are things that are really hard and immovable or hard to get around in a piece of software. This requires you to dive a little deeper into the architecture of a given piece of software. So think about a piece of software and how it might scale. What are the things that go into this? When you're talking about scale, you're going to talk about single node versus distributed versions of things. A distributed version may have extra restrictions. Like, so what happens when you shard your data out across many machines and you have the many nodes on many machines? What does that mean? Does it restrict on how you can use it? Does it restrict on the accuracy of the results? These are walls that you have to understand. Often, most software also has things like hard limits. The hard limits might be a specific size of data that you can handle in a given entity and atomic entity of data. So, for example, in Elasticsearch, I think the single document limit is 2 gigabytes, right? But you'd never want to use that. That's a hard limit. The soft limit is much smaller. Redis had something like 512 megabytes as the key, and that would be a ridiculous thing to do. So understand the difference between the hard limit and what's practical. That's important to know. So the hard limit is a wall, and the impractical thing can be thought of as a virtual wall. You don't want to cross that line. And then think about things as it comes into how they execute. For example, single-threaded versus multi-threaded applications, and how that might affect your scaling. Are you going to saturate something else besides CPU? Or are you going to saturate network availability, right? So most instances when you're running in the cloud these days have some sort of network ceiling, and are you breaching prematurely that network ceiling when you have plenty of computation available? These are all things to keep in mind. So these are the walls. So when you're evaluating how you're going to scale, know where your walls are. Understand the axis of time. Now, the interesting thing I think about software is it doesn't wear out, right? Unlike a bridge or something else, it tends to wear out. Software doesn't wear out. And sometimes you can get software that runs for decades and decades and decades. I did some research and saw that there is some software used by the Department of Defense as of 2016 was still being used. I don't know if it's currently being used, but the software was originally written in 1958, right? Now, that is a huge exception. There are a few industries that have kind of fundamental things that don't change very often. You're talking about things like financials, banks, governments, telecoms. These can have software that runs for a very long time. However, the majority of software runs for actually a relatively short amount of time. So it can either have a couple different paths. It can be used for that short amount of time and then replaced as business needs change, or it can evolve over time and as business needs change. Now, here's the thing to keep in mind when you're talking about scaling. When you're building software that goes from small to large, or from large to small, but we'll talk mostly about going upwards, you have to understand what the implications are of building software that can scale to massive amounts. Now, that can take a lot of engineering effort, and that's fine, but think about how long that's going to last. If, for example, it takes you 1 year to develop a piece of software that will only be used for 5 years, is that an efficient use of time? Or will you reevaluate every 5 years or so and figure out that you're going to have to build new software or keep where you're going? So you can kind of trade agility of software development, small a agility, for lifespan of the product, right? You could build something that might last 20 years, but that might require a larger upfront engineering effort. And it may not be worth it if you're not going to scale in a given time. It may be worth it to write something quick and dirty and then write it again a few months or years later as you understand your access to time and how scale will affect it. So don't assume that everything is going to be existing for 40 years forward. Now, I'm not a civil engineer by any stretch of the imagination. It's interesting to me. I think part of the reason it's interesting to me is I have civil engineers on like all sides of my family, and it's a very different discipline than software engineering or software development. Um, they have many different things to think about. Some software, of course, is um, uh, dependent on, a bad piece of software will cause um, uh, life loss if it's written incorrectly, but the majority of software isn't in that category. And civil engineering has to deal with that every day. The other thing that civil engineering has to deal with is this idea of balancing inputs, so raw materials, versus cost and lifespan, right? We have different things that we have to worry about in being a good engineer and engineering our software well for scale. Our primary input for at least this is not necessarily tons of concrete. It is actually human effort. And the amount of energy we use to type in the source code or to have the build scripts in deployment scripts, very small. But the engineering effort can be pretty profound. So the thing I like to kind of say, what can we borrow from these? And could we, as software engineers, build a good bridge? We'd have to think about different things. We'd have to think about scale in a little different way. We think about scale as actually using the right amount of software, the right type of software. These sorts of things can go in to create a better bridge. Now, engineers could build a bridge out of tons and tons and tons of concrete, and it might work fine, but that wouldn't be a good engineering task. They try to right size things. And as we are thinking about scale, we need to think about right sizing scale rather than just building massive complex systems. Overall, a right size system will work very well. We need to think about these things and not pay attention to the trends that are happening that may be influencing us to overbuild our software or underbuild our software. So when we think about this, I would say borrow the ethos of the civil engineer, build just enough to get the job done to meet the requirements, and to make sure that you are building something that will last the right amount of time. So that's kind of where I come from as far as scaling. I hope you found this useful. And think about building a bridge when you're planning your next software project and thinking about how the scale might happen. Do you really need to build the George Washington Bridge for the 2 or 3 people that are going to cross your software every day? Or can you get away with building a rope bridge that'll work just fine? Think about these things. Sometimes you're going to need one versus the other, of course, and hope you enjoyed this talk. So please connect with me on social media. You can be found on Twitter at the location on screen and on LinkedIn. I'd love to hear from you. Thanks so much. Bye-bye.